nonlinear algebraic equations. These methods were classified into two main classes. One was bracketing method and the other was open methods. Bracketing methods basically bracketed the solution of our interest, whereas the open methods worked either with one or two solutions, and the two solutions may not necessarily bracket the two guesses may not necessarily bracket the true solution. So that was our bracketing and open methods. Then we looked at basically implementation of these methods using Microsoft Excel for one particular example. What we are going to do in this lecture essentially is to look at some of the three specific methods out of the methods that we have done in the previous lecture, and try to do a more in-depth analysis of the convergence of these methods. So what do I mean really by convergence is this, is what we said is each method is going to start with an initial guess, let us call that as x1, and then we are going to use some method to get xi plus 1 equal to something in order to get from basically either from xi or from xi and xi minus 1. For example, in case of bisection method, what we had was xi plus 1 was equal to xl plus xr divided by 2 was in case of bisection. In case of a fixed point iteration method, we used xi plus 1 as nothing but g of xi and if we look at the Newton-Raphson method, we have xi plus 1 equal to xi minus f of xi divided by f dash of xi, that was Newton-Raphson. Okay. And in likewise we had secant method, and secant method we had xi plus 1 equal to xi minus f of xi multiplied by xi minus xi minus 1 divided by f of xi minus f of x I minus 1. This was Reguli-Falsy or secant method. Okay, of course, the difference between Reguli-Falsy and the secant method was in Reguli-Falsy we have this as xl and xr instead of xi and xi minus 1. So these were the methods that we looked at in our previous lecture. What we are going to do is take these three specific methods and we are going to analyze how these particular methods converge. What we mean by that is the next step beyond this, what we looked at was when to decide whether or not to stop this particular procedure of iteratively finding out xi plus 1 starting with xi using any of these methods mentioned over here. So the idea over there is that as the index I keeps increasing, we need our x to somehow go to the true solution x bar. Okay. So let us again go back and think about the definition of errors that we had come up with earlier. The definition of true error et at let us say the ith iteration is going to be xi minus x bar, where x bar is the true solution, and our approximation error e is going to be equal to xi minus xi minus 1, and of course we do not bias ourselves whether this error is positive or negative. So we are going to put we are just going to look at the absolute values of these particular errors. Okay. So this is the error at iteration I whether we are looking at the true error or the approximation error. So as we go from I equal to 1 to say I equal to n, where n is a big enough number, we want our xi to start converging towards x bar, okay. And in the limit that n is equal to infinity, we really want our xi to actually represent our x bar. That is what our aim in a numerical technique is going to be. So the convergence criterion that we are going to look at is how basically our ei plus 1, how ei plus 1 depends on ei, or for that, and then ei then is going to depend on ei minus 1 and so on up to E1, that is the error in the initial condition that we started out with. So we start out with a fair amount of error in the initial condition, and as the number of iterations increase, we have this particular xi or xi plus xi tending towards some solution x bar, okay. And since in general x bar is not really known, the stopping criteria we actually use is not based on the true error, but it is either based on the approximation error ei, or the stopping criteria is based on the approximation error epsilon I, which is nothing but ei divided by xi, okay. Again, these error concepts were considered earlier in module 2, and this is what we are interested in. So for all these methods we are going to look at how ei plus 1, how that depends on ei, okay. So that is essentially what we are interested in doing. So now let us take the bisection method example. And I am taking the bisection method the first simply because it is the easiest of the methods for us to analyze. That is the reason why we are taking the bisection method, and at any time, at any iteration I, we get xi plus 1 as nothing but xl plus xr divided by 2, an average of our left guess value and of the right guess value. These two values, again to recall, are going to bracket the true solution, okay. So this is how we are going to get our xi plus 1. So geometrically what that means is basically this is going to be our xl, this is going to be our xr, and this is going to be our xi plus 1, okay. Our error ei plus 1 is going to be nothing but the absolute value of xi plus 1 minus xi, okay. Keep in mind xi is either going to be xl or it is going to be xr. So xi is either going to be equal to xl or it is going to be equal to xr. It really does not matter if we substitute this particular expression xl minus plus xr divided by 2 minus, let us for now just substitute xl over here. What we will get this as, this is going to be nothing but xr minus xl divided by 2. If we substitute xr over here, we are going to get xl minus xr divided by 2. Since we are taking the absolute value, this is going to be the actual error is going to be exactly the same. It is going to be the difference between the two solutions and half of that, okay. So what does xr minus xl mean? Xr minus xl is nothing but this particular length, that is what our xr minus xl is going to be, and xr minus xl by 2 is going to be essentially this length, or it is going to be this length, okay. So this, for example, is nothing but our ei plus 1, okay. So to summarize, at any given iteration count I, the next error ei plus 1 is going to be just the half the length of the current segment from xl to xr. Okay. So that is what this is essentially going to be. So now let us look at where we have started this particular problem. We start this particular problem by giving two initial guesses which lie on either side of the true solution. So let us say this is the entire line segment where we started out with the two initial guesses. At the first iteration, so we started with x0 and x1. At the first iteration, this is where we got our x2 at. Okay. So at the first iteration, perhaps the length segment where when we started out with now has been halved after the iteration number 1. So let us just consider that initially the difference xl minus xr that we started with was that particular length was L. After the first iteration, this length became L by 2. Okay. Now in the second iteration, we get our x3 as again the midpoint over here. Now let us say in this particular, let us argue that in this particular occasion it is the xl that is dropped, x3 becomes equal to xl. In that particular case we will get this particular segment, irrespective of whether we retain the left half of the segment or the right half of the segment. We have essentially half the length that we are interested in. So this essentially has become L by 4. At the end of the third iteration, the length of the segment has become L by 8 and so on and so forth. Okay. So we started out with x0 and x1. Let's write that down, and I will use a different colored chalk here. We started out with x0 and x1. Okay. This remains our x0, this becomes our x2. Now we have x3 and x2, and now we have x3 and x4. Okay. So the initial difference that we really started out with was x1 minus x0, that is nothing but our E1, or so E1 was equal to L. So that is what I am going to write down over here. Okay. Our E2 is then this particular difference, our E2 was nothing but L by 2. E3 was L by 2 squared, and so on. Our E I plus 1 was nothing but L divided by 2 to the power I. Okay. So this is the error in the current iteration of the bisection method, and as you see that as the number of iterations of the bisection method increase, every time we are going to halve the particular error that we have. Okay. So this is essentially what we are going to get in bisection method. The final error E I plus 1 is going to be just the initial length L divided by 2 to the power I. Okay. Also we are interested in seeing how the error Ei plus 1 is related to the error Ei, and that is very simple to know, because Ei is going to be nothing but L divided by 2 to the power I minus 1. So we will be able to write Ei plus 1 is nothing but Ei divided by 2. Okay. So these are the two important expressions, and they essentially mean one and the same thing with respect to convergence of a bisection method. So these are essentially two important expressions to keep in mind. This particular way of convergence is what is known as linear convergence. So the bisection method has a linear rate of convergence. what we mean by linear rate of convergence, or in general what we mean by rate of convergence, is how our EI plus 1 is related to EI. So, EI plus 1 is some constant alpha multiplied by EI to the power n, or let us call it eta, just to distinguish from the total number of iterations. Okay. So, this particular eta determines the order of convergence of a particular numerical technique, whereas this particular expression gives the rate of convergence of this technique. So, what that essentially means is how the error in the I plus 1th iteration is related to the error in ith iteration. If eta equal to 1, we call this as a linear rate of convergence. Okay, and this is what we really get for the bisection method. EI plus 1 is nothing but half, that means alpha equal to half multiplied by EI to the power 1, and so in this particular case eta is equal to 1 and we get a linear rate of convergence. Okay, in a few minutes from now what we will look at is also look at fixed point iteration, which also has a linear rate of convergence, and the Newton-Raphson method, which has a quadratic rate of convergence. So, what that means by quadratic rate of convergence is that eta is equal to 2. The two methods that we are not going to cover, the derivations of are the the Regulai-Falsey method and the Secant method, and in both Regulai-Falsey method and Secant method the eta lies essentially between 1 and 2. Okay. So, that we call as a superlinear rate of convergence. Okay, but coming back to where we were at, for the bisection method we have eta equal to 1 with linear rate of convergence. What is another advantage of bisection method is that given a particular tolerance value, we can determine a priori how many iterations we are going to require for this particular method to converge. For example, let us say epsilon tolerance is going to be the desired accuracy that we are interested in, or we will write that as E tolerance as the desired accuracy that we are interested in. So, the bisection method is said to have converged when E tolerance is EI plus 1 is less than E tolerance, and we are going to start with the length L. So, our EI plus 1 is nothing but L divided by 2I, so that is going to be less than E tolerance. Okay, and we take our 2 to the power I on the other side, we will essentially get I and divide by E tolerance and take a logarithm, we will get I equal to log of ln divided by E tol divided by log of 2. Okay. So, I has to be at least equal to this particular number or greater than this. This of course is a fraction. So, for example, if we get this particular number as 10.5, the minimum number of iterations of the bisection method we will require are going to be equal to 11, and we can predetermine how many iterations of bisection method we are going to require in order to solve this particular problem. Okay. So, that is essentially all we have to do about the bisection method. The next method that we are going to consider, and we will do the same kind of stability analysis on, and that is going to be a fixed point iteration. What I am going to do with fixed point iteration is again go through a derivation of a similar type. We will derive the expression how EI plus 1 depends on EI, and there we will again see EI plus 1 is some alpha multiplied by EI, and then what that particular value of alpha means with respect to the stability of that solution, we will talk about that, and then we will talk about the graphical interpretation of what that means. Okay. So that's coming up right now, is going to essentially fixed point iteration. Okay. So the objective in solving the fixed point iteration fixed point iteration was to get the solution of the equation x equal to g of x, and if x bar is the solution, okay, then x bar is going to satisfy this particular equation. So x bar is going to satisfy the equation x bar equal to g of x. X bar is going to be exactly equal to g of x bar. That is what we really mean by the true solution of that particular problem. Okay. So this, let us call this as our equation number 1. Okay. Now the fixed point iteration, the way that the fixed point iteration works is that we basically calculate our g of x at the current guess xi, and based on the current guess we are going to calculate the g of x, and that we are going to assign it to xi plus 1. So what we have again was xi plus 1 is going to be equal to g of xi, that's our equation 2, that's our fixed point iteration. Okay. So this is essentially what we are going to get. What we can just do is subtract equation 1 from equation number 2, or rather we will subtract equation 2 from equation number 1, and the result of that subtraction is going to be x bar minus xi is going to be equal to g of x bar minus g of xi. Okay. Now by essentially the mean value theorem, what this particular expression really means, what we can write this particular expression down as, we can write this as g dash of some value zeta, where zeta is a value that lies between xi and x bar. So g dash of this value zeta multiplied by the delta x, which is essentially going to be equal to x bar minus xi. Okay. So this is going to be our expression, sorry, this should have xi plus 1, when we have subtracted these two equations we will have x bar minus xi plus 1. So this essentially is nothing but our ei plus 1, and this guy is nothing but our expression ei, and we can write those things down. So we have ei plus 1 is going to be equal to nothing but g dash of zeta multiplied by our error ei. Okay. So the error in I plus 1th iteration is going to be some particular constant g dash of zeta multiplied by error at the ith iteration, where zeta is a point which lies somewhere between xi and x bar. Okay. And as the error becomes smaller and smaller, our g dash zeta tends to go towards xi or x bar. So it is essentially what we really need to do in order to figure out whether this particular method is convergent, this particular what this particular value is going to be is calculate the first derivative of the function g of x at the value xi. What we are saying over here is xi is close enough to the value zeta, and that will essentially give you how this particular method is converging from as the number of iterations increase. Okay. So what do we mean by that is, again let us look at our expression ei plus 1 equal to alpha times ei, where alpha in this particular case is g of zeta and sorry g dash of zeta, and rather I should be writing g dash of zeta I, because zeta I is a number that lies between xi and x bar. Okay. Likewise we will have the expression ei is going to be the same constant alpha multiplied by ei minus 1, so on and so forth. So that we can write as alpha squared multiplied by ei minus 1, right, because ei is nothing but alpha multiplied by ei minus 1, and alpha multiplied by alpha would be essentially also alpha squared into ei minus 1, and if we keep writing that over and over again, we will get this as alpha to the power I multiplied by E1. Okay. So this is going to be our EI plus 1. Okay. Now if this particular value alpha is lies between minus 1 to plus 1, alpha to the power I decreases continuously, and as I tends to infinity, alpha to the power I is going to become equal to 0. Okay. So if minus 1 is going to be less than alpha less than 1, then the fixed point iteration converges. Okay. And if alpha lies is greater than 1, or if alpha is less than minus 1, in other words if the absolute value of alpha is greater than 1, then the fixed point iteration is not guaranteed to converge. Okay. So just to summarize, what alpha is nothing but g dash of zeta, and we are going to approximate zeta as our xi. So to summarize, our fixed point iteration has linear rate of convergence and it is guaranteed to converge if our absolute value of g of xi is less than 1. Okay. So this is the important result that we get about convergence of the fixed point iteration method. Okay. So what we are going to do is we will take up an example in Microsoft Excel and try to use basically the fixed point iteration in order to get the solution to that particular expression. The expression that we are going to use is f of x equal to 5x minus e to the power x by 2. Okay. And f of x in this particular written in this particular form, we can write this in two different ways. So f of x is equivalent to this equal to 0, and the two equivalent ways that we can write this is we can take e to the power x by 2 onto the other side and divide by 5. So our g of x for the first case is going to be nothing but 1 by 5 e to the power x by 2, and in the second case we take this to the left hand side to the right hand side and take a logarithm on both sides, and we will get our x is going to be equal to 2 times log of 5x, okay. That is going to be the second approximation, second way of getting g of x, okay. So what we are going to do essentially is consider these two examples. These two ways of solving this particular problem using the fixed point iteration method, okay. So we are now going to move on to Excel in order to look at the fixed point iteration. Okay. So just to give us an idea of what this particular function looks like, what I have done over here is I have taken, so this is the particular equation 5x minus e to the power x by 2 equal to 0, that is what we want to solve. So the left hand side of this particular expression is nothing but our function f of x. So for various values of x going from 0 to 8, what I have done is plotted our f of x, and if you click F2 you will be able to see what f of x means. It's basically 5 multiplied by C2. C2 is nothing but, as you can see over here, C2 is nothing but our x value minus e to the power x by 2. Exp is the exponential, C2 is again x divided by 2. So that is our function f of x, and what then I had done is just dragged it along the entire column, and when I dragged it along the entire column and then plotted, this is what we get as a solution of f of x as a function of x, okay. So this particular function intersects the x axis at 2 points. These 2 points are the points of solution. So what we can do is we can just format the data series and add a line. Okay. So if you look at this, this is one solution, and that solution is lies between 7 and 7.5, perhaps something like 7.1, 7.2 or something like that, and then there is another solution which lies essentially between 0.2 and 0.3, that is when the function changes the sign, and so this is perhaps going to be something like 0.22 or something of that sort, okay. So now, as we had said before, this particular equation can either be written as, so this we will write as 5x equal to exponential of x by 2. I will just increase the font. Okay, so 5x equal to exponent of x by 2, we can either divide this particular expression by 5 to get our first example of g of x, and when we do that, this is what we get g of x. The equation that we want to solve is x equal to e to the power x by 2 divided by 5, or the other way to do this is take a logarithm. So you will have log of 5x equal to x by 2, or x equal to 2 times log of 5x, and this is what we have gotten in our second expression over here. So x equal to 2 times log of 5x. Okay. So now, as we can see, this particular curve intersects the x axis at 2 points. What we will do is we will solve the fixed point iteration method using the first expression, that is x equal to 1/5 e to the power x by 2. We will solve that particular expression starting with various different initial guesses between 0 and 10. The areas of real interest for us are the areas where x is going to be less than the particular solution, this particular solution. The second area of interest is going to be when x lies between this solution and this solution, and the third area of interest is when x lies beyond this particular solution. Okay. So let us look at the first example, x equal to e to the power x by 2, and I have used the various iterations over here just to keep it consistent with the notations we have used previously. I will start I with I equal to 1. Okay. So essentially let us start with in the beginning, let us start very close to 0, let us start with a number equal to say 0.00001, okay. And when we start with a number equal to 0.001, what we see is that fairly quickly our solution goes and converges to this particular point, okay. So we start at this particular region. So what I will do over here is I will just zoom this, okay. So this is the same curve, okay. I have not done anything to that curve. What I have, the only thing I have done is zoomed in the x and y axis in order to show you what exactly happens in the x and the y axis, and this is our x axis, and this is the point of intersection. So when we started with some value very close to 0 over here, what happened with the fixed point iteration was that particular value ended up going to this particular solution when we used x equal to e to the power x by 2 divided by 5, okay. So now let us take a value very close to the solution, but again on this side of the solution let us take the value as 0.2, okay. And if our error criterion was 10 to the power minus 4, it has taken about 6 iterations in order to converge the solution to the predefined error criterion. Let us look at what happens when our initial guess is x equal to 0.2. What we find when the initial guess is x equal to 0.2 again is that the solution converges to the desired solution, and the solution converges fairly quickly. It converges now this time in 5 iterations, okay. And again starting from here we have ended up at this particular solution. Let us go a little bit further and start at 0.5 and see what is going to happen. So again I will change this particular number to 0.5, and so from 0.5 we ended up at 0.25, 0.22 and so on. So what we did is from this particular point we had a big jump and we ended up over here, and then fairly slowly we ended up to this particular solution, okay. Let us now again zoom out by this particular system. And over here also, okay. So now we have gone beyond that point, and let's go somewhere close to say 4, and we will start with that. Instead of 0.5 we will change x equal to 4. Again what we find is that the solution has indeed converged, okay. And let us try again x equal to say x equal to 7. X equal to 7 is fairly close to the other solution, and when we substitute x equal to 7 again we find that the number of iterations taken are fairly large, but again what we find is that our solution has indeed converged from starting at this particular value. Although we have started very close to this particular solution, irrespective of that, when we started at this value we ended up going essentially to this particular guy, okay. So that is what has happened for this entire range. What we have done is we have spanned the entire range from x equal to 0.001 to x equal to 7, and for this entire range we get this, the fixed point iteration method converges to this particular solution. Now let us see what happens if we go to point 8, and what the interesting thing that we see when we get to x equal to 8 is now the solution is not converging, in fact the solution is diverging. The first value of x is x equal to 8, the second value of x is x equal to almost 11, 47, 3 into 10 to the power 9, and then there is a floating point error because the numbers have become too large compared to the storage capacity. Essentially the number has become greater than 10 to the power 309, okay. So that is where essentially this particular method stops working. So in a sense when we started with x equal to 8, rather than converging to this particular solution we ended up diverging towards infinity. That is what this method shows. Okay. Now our g of x was nothing but e to the power x by 2 divided by 5. Okay. So g dash of x was nothing but e to the power, so g of x was exp x by 2 divided by 5, and g dash of x was exp x divided by 2 divided by 10. Okay. So this were our g of x and g dash of x values. So now when we started off with the value of 8, well, let us substitute that particular value and see what we get. So that is equal to exp of 8 divided by 2, the whole thing divided by 10, we get that value as 5.4. So what we essentially see over here, that the exponential that the g dash of x computed at that particular value is essentially greater than 1, which basically means that this particular method is perhaps going to diverge. Let us look at the another case when we started with say 0.001. So if we do exp of 0.001, what we find is that indeed that particular value is less than 1. So when we start with x equal to say 0.001, we are guaranteed to converge. When we start with x equal to 8, there is no guarantees of convergence. It is possible that the particular method will converge, it is possible that the particular method will not converge. And just to take an example, if we were to replace this with 4, so exp of 4 by 2, that is going to show us convergence. So the convergence is, so if we were to use our particular initial guess in this range between 0 to say 4.2 or 4.3, we are definitely going to get the solution to converge. So we know that for a fact that for from x equal to 0 to x equal to say around 5, we are going to get the solution to converge. But what happens when we substitute 7 in this particular expression? When we substitute 7, our g dash x evaluated at x equal to 7 is indeed greater than 1, but as we had seen when we had 7 in this particular expression, our fixed point iteration converges. So what does that mean? What it really means is that the absolute value of g prime of x lying between -1 and +1 is a sufficient condition for convergence, but it is not a necessary condition. So that means if g dash of x lies between -1 and +1, we know for sure that this particular method is going to converge. But if g dash of x does not lie between -1 and +1, there is a possibility that the method will converge, but there is also a possibility that the method will not converge. So we cannot really say anything for sure if g dash of x is going to be greater than 1, but if it is less than 1, or rather if it is between -1 and +1, we can say with 100% certainty that the method is going to converge. Okay. The other way of writing 5x equal to e to the power x by 2 is by taking log onto the both sides and then multiplying by 2 throughout. So we will have ln 5x equal to x by 2, and then we can write x equal to 2 times of ln 5x, and when we do that, and then we can run the fixed point iteration. So it is the same expression as you see over here. It is exactly the same expression that we have solved previously. Only thing is that we have rewritten x equal to g of x in the form x equal to 2 times log of 5x. Okay. So again iteration number 1, 2 and so on, this is to keep up with the notations that we have been using previously. Okay. This is our x, this is g of x. I will just show you what g of x is. It is 2 multiplied by log of 5 multiplied by b6, b6 is nothing but x. Okay. And so if let us say we start with a very low value, let us say we start with a value of say 0.2, what is going to happen in this case? If we start with a value of 0.2, the g of x that we will get is equal to 0, and then log of 0 is not defined, and therefore we cannot continue further. So if the particular initial guess is say at 0.2, we are not getting the solution to converge. Let's see if it was say 0.22, again this solution is not converging. So for all the values beyond this particular solution, our numerical method of fixed point iteration is unable to converge. If we use the value of 0.3, this value of 0.3 is fairly close to this particular solution, but when we start with the value of 0.3 with the second expression for this fixed point iteration, that particular method converges to this particular solution and not to this solution. Okay. And that is what happens if we take the value equal to 4, again we are converging. If we take the value equal to 7, again we converge, and if we take the value equal to 10, again we see that we are converging to the solution 7.15, which essentially means that from this range onwards right up to infinity, no matter where we start off with that particular form of fixed point iteration, we will end up at this case. Okay. And what you can then try yourself is for this g of x 2 log 5x, you can get g dash of x, and once you really have g prime of x, then find out numerically where the fixed point iteration is guaranteed to converge and where the fixed point iteration does not have guarantees to converge. And what you will see essentially from this particular example is that the fixed point iteration has a guarantee to converge in this entire range starting from approximately 4.2 and going right up to infinity, whereas in this range there are no guarantees of convergence. But we find that in spite of the fact that there are no guarantees of convergence, because this is a sufficient condition, as a result of this we could get convergence if g prime exceeds 1 or is less than -1. Okay. And then the final thing is what we can do is plot our error against the iteration number. I will just do this particular plotting over here, and I will essentially try to plot this on a log scale, and we will have to go away from this, insert scatter plot that we will insert. Okay. And so what we are going to do is we are going to make this plot as a logarithm plot. Our y axis is going to be a logarithmic scale. Okay. So when we essentially make this particular scale as a logarithmic scale, we find that that particular error line is a straight line approximately. Okay. And so this particular curve is going to be essentially a straight line with a slope of -1. Okay. What why we get that is essentially because we have a linear rate of convergence. By linear rate of convergence we mean the error ei plus 1 is essentially going to increase linearly with the number of iterations as the number of iterations increase. So ei plus 1 is going to be equal to some constant multiplied by ei to the power 1, and then when we take a logarithmic plot of that, we are essentially going to get an approximately a straight line in this particular case, an approximate straight line with a slope of -1. Okay. So that is about the fixed point iteration. Similarly, if we look at the bisection method, we will also get a similar logarithmic plot for how the error changes with respect to the number of iterations. Okay. what we are going to do next is, we are going to look at the Newton-Raphson's method. We will derive the Newton-Raphson's method based on essentially the Taylor series expansion, and then we will use the Taylor series expansion in order to figure out how the errors in the Newton-Raphson's method change with the iteration.